Okay? Now, when you are having this kind of shape, you are having this streamline shape, right? And you take flow, working on it. Okay? So when you have a flow like this, there will be, I will not take that component, I will take one point over there. The flow is coming like that, right? When the flow is coming like that, it will have the normal component and it will also have the tangential component. So this one is the Ft, this one is the Fn, and this one is your force. Now thinking about the normal force, if you look at the x and y, these will provide Fn, y, and over there, right? Because it's going there. Actually, the Fny will be goes down in this case. When you look at it, the Fny will goes here. This is your Fny, and this one, because this is your Fn, right? This one is your Fnx. These contribute to the drag. This one contribute to the lift. In this case, it is negative lift. It goes down. Now we are talking about the Ft, the tangential, right? The tangential. The tangential, if you look at it, it provides Fty, goes up, and Ftx, which is same with Fnx. So you see, this one is your drag, this one is your negative lift, this one is your positive lift. That's why you got all these things. And since it occurs in all, so you need to integral it. Take the integral of it overall. Okay, so you take 1. Any question about that? One single force, you split it into tangential and normal, and then from those, you split it again to the y direction and x direction. So you get lift and drag. Okay? So, how does it help our life? Because of this knowledge, we were able to develop such an engineering miracle, right? That we can bring those heavy, big, fat aircraft flying to the air, right? Because of that. Okay? And don't get it wrong, even though this thing looks like a cylinder with no purpose other than bringing all the component, I mean, like, you most of the time put everything inside, right? This is not only for that purpose, this thing also provides some lift. So this thing is providing lift on top of this thing. Big. Okay? Okay, so we will study this section in the theory of airlift, lecture 12. Okay? So, now, again, your imagination, because we are not in the swimming pool. Imagine you are walking in here now, right? Because here you have air. Do you feel the friction on your body? No. When you do the same within the swimming pool, how do you feel? Go to the swimming pool, you'll be there, submerged, and then try to walk. Can you walk easily like what I did now? What I'm doing now? Cannot. Why? We are not talking about drag force. Why it is different? Buoyancy, drag force, pressure, density. Yeah, I just want to hear that one. The density of the fluid is different, right? The density of the fluid is different. Now you do this, right? And you do this. Do you feel the difference?
Yes.
Why it is different?
Speed.
The speed or velocity. Okay, so now you have density, you have the velocity. Okay, if you bring a sports car like Ferrari and you bring a truck, mining truck, do you think the drag will be the same? No. So it depends on the shape, right? On the shape. So density change, everything will change. The drag will change. Shape change, drag change. What else? Velocity change, the drag will change also. How about if you compare water and oil? Both has the same density, roughly about 900. Do you feel the same or different? Anyone walking within the oil? Inside the oil? You try to walk. How do you know it is different? No. You can ask fish who live in the Gulf of Mexico, right? Because they have oil spill before, so they know how it feels to swim in the oil. So, but we know it will be different because the viscosity is different. Okay? Since it depends on so many things, right? Since it depends on the velocity and so on and so on and so on, it is mostly impractical, okay, impractical to express it in terms of force. Okay? Any one of you buy a car and the car manufacturer says, okay, you know what? If you buy this car, the force, the drag force you overcome with this car is 9,000 Newton. No, right? But if you buy, at that time, I still remember when first Beza was launched, they said that it has the lowest friction factor or friction coefficient in Malaysia, which is 0.32. So, rather than present it in terms of drag force, you need to present it in terms of the drag coefficient. Why? Because this drag coefficient is unitless, so it does not depend on those parameters. Regardless of your velocity, regardless of your density, regardless of your area, this will remain the same for the same thing, right? That's why we work with this CD and CL, right? How you derive it? The CD is the drag force divided by, what is this? Dynamic pressure area. Right? What is this area? What area is this? This one is the frontal area. Okay, now I have to tell you the difference between those area and the other area. When we are talking about this total drag, you are talking about the frontal area. But later on, when you are talking about the shear force, you are talking about this area, not this area. When you are talking about shear force working on this area, right? But when you are talking about pressure force, you are talking about this area, not that area. Yeah? Good. Okay? That's why if you have the big car, okay, the frontal area getting bigger and your force, the drag coefficient will be higher. Okay, even though for the same drag coefficient, you know, like Tesla semis, they claim that their drag coefficient is lower than Lamborghini. Right? They claim. Sure, they claim. But since Lamborghini is shorter, it's wider but shorter, so at the end of the day, your area will be smaller. When your area is smaller, of course, your drag force will be smaller. Even though you have bigger, so you have to be careful with that. The same goes for the lift. Some aircraft having a smaller wing, but they can bring heavier load. Why they can do that? Because their CL is bigger. So it depends on